Our Sun, a life-giving star at the center of our solar system, holds a fate far grander and more dramatic than simply burning out. The Sun, like all stars, has a finite lifespan fueled by nuclear fusion. In about 5 billion years, it will enter its final stages and dramatically transform our solar system. Here's a detailed look at what will happen to our solar system when the Sun dies. 1. Fuel depletion. Over billions of years, the Sun's core has been slowly converting hydrogen, its primary fuel, into helium through a process called nuclear fusion. This fusion releases tremendous energy, powering the Sun and providing light and warmth for our solar system. However, this process is not infinitely sustainable. Like a car using up its gas tank, the Sun's core is gradually running out of hydrogen. The rate of fusion slows down. This slowdown has several consequences. Reduced energy production. The decreased fusion rate translates to less energy being produced in the Sun's core. This reduction impacts the Sun's overall energy output, eventually affecting the entire solar system. 2. Red giant transformation. As the Sun depletes its hydrogen fuel and the fusion rate slows, the core starts to contract and heat up. This increase in temperature triggers a crucial event, the ignition of hydrogen fusion in a shell around the core. This shell burning releases energy, but it's a less efficient process compared to core fusion. Consequently, the energy released pushes against the outer layers of the Sun, causing them to swell dramatically. This expansion is what transforms the Sun from its current yellow dwarf state into a red giant. Here are some key features of the red giant phase. Massive size. The Sun's radius can increase to hundreds of times its current size, potentially engulfing the orbits of Mercury and Venus. Although the Sun's overall size increases, its surface temperature actually becomes cooler due to the larger surface area it needs to heat. This is why it's called a red giant rather than a hot giant. Luminosity increase. Despite the cooler surface temperature, the Sun's total energy output actually increases due to the much larger volume involved in fusion. However, this increase is not enough to compensate for the Earth's potential fate as described in subsequent points. 3. Inner planet demise. As the Sun transitions into a red giant, its expanding outer layers become much less dense. This poses a significant threat to the inner planets, particularly Mercury and Venus, due to the following factors: increased gravitational pull. While the Sun's overall mass remains roughly constant, its enlarged envelope creates a larger gravitational field. This stronger gravitational pull acts on the inner planets, tugging them closer towards the Sun. Tidal forces. The Sun's gravity isn't uniform across the planets. The side of a planet facing the Sun experiences a stronger pull than the side facing away. This difference in gravitational forces creates tidal forces that can stretch and deform the planet. Heat and radiation. As the Sun gets closer, the planets experience a significant increase in both heat and radiation. This intense radiation can strip away a planet's atmosphere and melt its surface, potentially rendering it uninhabitable. The combined effects of these factors are likely to be devastating for the inner planets. Mercury, being closest to the Sun, is almost certain to be engulfed by the expanding atmosphere. Venus, due to its closer proximity and strong tidal forces, might also face a similar fate. Even if not completely engulfed, the extreme heat and radiation from the red giant Sun could vaporize the atmospheres and melt the surfaces of these planets. 4. Earth's uncertain future. While the inner planets face certain doom during the Sun's red giant phase, Earth's fate is a bit more uncertain. Here's an explanation of the potential scenarios. Tidal locking. Another possibility is that Earth becomes steadily locked with the Sun. This means one side of Earth would permanently face the Sun, experiencing intense heat and radiation, while the other side would be in perpetual darkness and extreme cold, which is unsuitable for life as we know it. Boil away Earth's oceans. Liquid water, crucial for life, cannot exist at temperatures exceeding 100 degrees Celsius, 212 degrees Fahrenheit, at sea level. The increased heat could cause the oceans to boil away, leaving behind a barren, rocky planet, destroy the atmosphere. The intense radiation could strip away Earth's protective atmosphere, exposing the planet to harmful solar radiation and further increasing the surface temperature. 5. Planetary nebula formation. As the Sun enters the final stages of its red giant phase, its outer layers become increasingly unstable due to the intense energy output from the shell-burning process. This instability leads to a dramatic event, the expulsion of the Sun's outer envelope. Here's a deeper look at this process. Mass ejection. The Sun's outer layers, rich in hydrogen and helium, are ejected into space at a relatively slow speed, around 10 to 20 kilometers per second. This ejected material forms a vast, expanding cloud of gas and dust called a planetary nebula. The formation of a planetary nebula marks a significant turning point in the Sun's life cycle. It signifies the end of the star's ability to sustain fusion in its outer layers and paves the way for its dramatic transformation into a white dwarf. 6. Helium Flash. After the Sun has shed its outer layers and formed a planetary nebula, an explosive event occurs within its core. Here's a closer look at this critical stage, that is helium ignition. The Sun's core, now primarily composed of helium, has been unable to initiate helium fusion because of insufficient temperature and pressure. This sudden pressure drop allows the helium nuclei to overcome the energy barrier and fuse together through a process called the triple alpha process. 7. Planetary nebula ejection. Following the brief but intense burst of energy from the helium flash, the Sun undergoes a dramatic transformation, the expulsion of its remaining envelope. The relentless radiation pressure from the core eventually overcomes the gravitational pull holding the Sun's remaining envelope together. This leads to the violent ejection of the envelope into the surrounding space at a much higher speed, around 100 to 200 kilometers per second, compared to the earlier mass loss. 8. White dwarf birth. After the dramatic expulsion of its outer layers, the Sun transforms into a white dwarf, which are considered as stellar remnants, meaning they are the final evolutionary stage for stars like our Sun. They are not massive enough to undergo further fusion reactions and eventually fade into cold, dark objects known as black dwarfs. The birth of a white dwarf marks the end of the Sun's active life as a star. 9. Loss of oceans. Earth's oceans will boil away, leaving behind a barren rock. As the Sun approaches its red giant phase, the increasing heat and radiation will have a devastating impact on Earth, leading to the boiling away of its oceans and transforming our once blue planet into a barren rock. This will cause the average global temperature to rise steadily, eventually exceeding the boiling point of water, 100 degrees Celsius or 212 degrees Fahrenheit, at sea level. Oceanic evaporation. With temperatures exceeding the boiling point, Earth's vast oceans will begin to evaporate at an accelerated rate. The loss of oceans will have catastrophic consequences for life on Earth. Oceans are not only home to a diverse array of marine species but also play a crucial role in regulating Earth's climate and providing atmospheric moisture. 10. Outer planet effects. The increased radiation disrupts the outer solar system, potentially melting ices on moons like Europa. The Sun's transformation into a red giant will not only affect the inner planets but also have rippling effects on the outer reaches of the solar system. As the Sun expands and becomes a red giant, its luminosity will increase significantly. This translates to a dramatic increase in radiation reaching the outer planets, including Jupiter, Saturn, Uranus, and Neptune. Impact on icy moons. This increased radiation poses a significant threat to the icy moons orbiting these gas giants. Moons like Europa, Jupiter, Enceladus, Saturn, and Triton, Neptune, are believed to harbor vast oceans of liquid water beneath their icy surfaces. The intense radiation from the red giant Sun could heat the icy surfaces of these moons, causing them to sublime, transition directly from solid to gas, or melt, potentially exposing the underlying liquid oceans.